Okay, perfect. Thank you. I should remove this. So, no, it's okay. It's better for the video. It's important. Okay, welcome everyone. Thank you for coming today in this very important day of negotiations, and for the next days are going to be even more uh, interesting to follow. But here today we have a little bit of input about science and what science says about Africa's disappearing glaciers. It's a presentation I put together with Georg Kaza, who is not here unfortunately today, but is an expert in researching and understanding Africa's remaining ice. So maybe some of you might be surprised to learn that there are actually some glaciers in Africa. And on this map, you see in black evidence of previous glaciations. So during the last glacial maximum or earlier. And in red, you see the last remnants of these glaciations. And these are regions, high mountains, mostly in tropical Africa, where we can find glaciers today. And you've probably heard of Kilimanjaro as the most famous one, maybe a little bit less about Mount Kenya and the Rwenzori mountains, which also holds a little bit of ice. And starting directly with the most important message of this presentation is that observations acquired from aerial pictures and satellites show that these glaciers have lost area continuously throughout the 20th century, from the late 19th century up to today, at an approximately constant rate. It's almost too constant, I would say, but the rate of decrease, as you can see here, the area is on the left as a square kilometer, and the entire 120 years of observation, so that the rate of decline varies a little bit between periods, but is very constant over time. What you can also see, so the zero area here on this line is available on all graphs. And although all started at a different starting area, you can see that by extrapolating this line, it's very likely that these glaciers are going to disappear over the next 10 to maximum 30 years. So these glaciers have acquired a lot of importance over time. They are really symbols of climate change. And in this presentation, I want to show why the picture and their importance is a bit more complicated than we might think. they have a strong symbolic nature, these glaciers. And so, as shown here, for example, by this 2014 photography project, where Simon Norfolk went to Lewis Glacier in Mount Kenya, and with photographic techniques, is displaying the location of the glacier in the late 19th century here. We have the present day glacier as photographed in 2014 and where the glacier was more than 100 years ago. And these pictures have really impressed people around the globe, showing the scale of the disappearance of this glacier. These are other examples of the retreat of the glacier over time. And these symbol pictures are very strong uh, ambassadors for disappearing glaciers. There is a small research station close to the glacier, which was also covered by ice 100 years ago. So more quantitatively, here this is a map of where the glacier was located in the late 19th century and where it is in 2010. And you see not only area, but volume also has decreased a lot over time. And this is going to be the case for most glaciers in Africa. And so we are going to go through a few examples here, and then we are going to talk about the science behind it. So this is the Lewis Glacier in particular, and a very high resolution satellite picture. And here you can see they accelerated over 2016, 2010, 2004. What worries also scientists here is that the glacier has disintegrated. So in the middle, there is no ice anymore. And once we have so little ice here, then other feedbacks are playing a role, such as heat emitted by the neighboring slopes are also helping the glacier to melt further. So there is no real hope that this glacier is going to survive in the near future. Let's go to Kilimanjaro now, which is probably the most famous one. And this is from close to the summit. And you can see that glaciers in Kilimanjaro are very special features of the landscape, very uncommon. If you have seen many glaciers in the Alps or in other regions, you are used to another picture. Then these actually really vertical walls and standing ice cliffs here. And I'm going to take this as an argument to say that glaciers in Africa are very, very different from all other glaciers we know in the world. And Kilimanjaro shows the same pictures. What you are seeing here are maps from photographs and satellites at different points in time, in 1912, 1962, up to 1984. And there is this regular decline of the area, 92, 2000, 2011, up to today, which is even smaller. So the same images now put all together in one map. It's a more graphical, maybe representations of the curves you have seen earlier today. And I could go on and go on. The picture is very similar for Rwenzori. You have seen the slides, but here again, a map representation of the extent of the ice and how it has declined over the century at a relatively constant rate. So before I go on now and we talk a little bit about the reasons for this ice decline, I want for this various audience here to make maybe a brief primer on glaciology and what we actually expect from mid-latitudes glaciology. I do this because you need to understand a little bit how mid-latitudes glacier work to understand that African glaciers are quite different from the ones we have in high mountain Asia, in the Alps, or in the Arctic. So this is a glacier close to where I live in Austria, Hintereisferner, and it displays the feature of a glacier which is not in a very good health, but still has some regions in the upper part, which we call an accumulation region, where snow from precipitation or avalanches is accumulating at the top of the glacier. This provides the mass input to what we call, scientists, a glacier, which is going then to move under the force of gravity once there is enough ice to start moving it, so to say. And so this is a typical mid-latitude glacier. And so represented a bit more graphically, we have a glacier here seen from the side. In the winter, and it's going to gain mass via accumulation, so frozen precipitation, snowfall. In the summer, it's going to lose mass, a process we call ablation in the scientific literature. And then we have an imbalance, mass gain at the top, mass loss at the bottom. And this going then to make ice move under the force of gravity from top to bottom to replace this missing ice. Gain at the top, loss at the bottom, a movement to replace it. Okay, and so this is a glacier which doesn't change in area. And so we scientists also like to add a new concept, which we call the equilibrium lunar altitude, which is a simplification, but still very useful representation of a point on the glacier where the mass balance is zero. So the glacier gains as much mass in the winter that it loses in the summer. And we like to use this to express the effect that climate change has on glaciers. For example, when this equilibrium lunar altitude in a cold climate is going to lower in elevation, we call this an ELA decrease, equilibrium lunar altitude decrease, and it's mostly representative of a colder climate because melt occurs lower and there is more accumulation at the top. And as a result, we gain mass in our glacier, and the glacier then is going to advance because there is more mass available, and also the glacier is going to move faster and move towards lower elevation. This is what happened in the Little Ice Age, for example, 150 years ago or earlier. And the same occurs now in the other direction, in presence of warming, less snowfall, more melt. The ELA, equilibrium lunar altitude, is going to rise. We have more mass loss than mass gain. The total balance is negative, and the glacier is going to retreat. And this is what most of the glaciers today are experiencing. The vast majority, almost 100%. Okay, so why am I talking about all this? Why are Africa's glaciers actually different? Well, they are so small nowadays, and they are located at very, very different locations than the mid-latitude glaciers. You've seen in the Hinterreisferner, the tongue of the glacier is located maybe at 2,000 meters altitude in a region where it experiences a lot of melt during the summer, positive temperatures. While most African glaciers are located very, very high in the atmosphere. For Mount Kilimanjaro, for example, it's close to 5,000 meters, so it's in a very complete different location in the atmosphere. And on Mount Kilimanjaro, glaciers are experiencing negative temperature all year long. And so melt doesn't occur the same way as it would do on the mid-latitude glaciers. And so maybe you're wondering if no melt can occur, so how can glacier even retreat? So this is what I'm going to try to explain in the next few slides. This is a symbolic picture, the same as before, glacier in the mid-latitudes, and the different arrows are not so important. I'm going to go through this in explanation. So this is what we call the energy balance of a glacier. A glacier receives energy from the sun, it receives energy from long-wave radiation, infrared radiation from the surroundings and from the atmosphere, and it loses energy as well via radiation, long-wave radiation itself, via exchange with the atmosphere above it. And all that, we scientists, we sum the numbers together and say, if it's positive for the glacier, then energy is given to the glacier and it's going to melt. And the melt then, as you can see on this image, is a result not only of temperature, but also on radiative fluxes. In a warming climate, both temperature and the radiative fluxes are increasing the melt. So now let's have a look at a typical glacier in the tropics in here on Kilimanjaro. So where the glacier has dynamically been separated from the plateau glacier, where ice cliffs have appeared and where we have very, very little melt, almost no melt, because the turbulent fluxes, the exchange with the atmosphere is actually very low. And so what we are going to see here is a completely different picture. Since I've said it already, the sun energy is so important for melting or giving energy to the glacier, we are going to see very large differences between a glacier which is dark, where ice is apparent, where sometimes also small particles on the glacier can be found. We call this a low albedo glacier, and then it's going to be able to retain much more of this energy. However, when snowfall comes onto this glacier, it provides a protective layer by protecting the glacier from the sun in the front like glass. And what we also see happening is that we have no ice cliffs, which are receiving energy in a very different way, nothing very usual and common for glaciologists like me who are more used to mid-latitude glaciers. But in the tropics, this is also going to be an important process. And here you have a new word, which is called sublimation. Sublimation is extremely important for tropical glaciers, which are located in very high elevation, in very dry conditions in the atmosphere. Sublimation is a little bit like evaporation. When you go out of the shower and you're wet, you are actually feeling cold a little bit because the water is evaporating from your skin. The same happens on tropical glacier, but it goes directly from the ice phase to the vapor phase. And it does that at the interface. And for this effect to happen, you need ice to be close to you need the ice to be close to a very dry atmosphere, and you need enough energy for the sun to provide this energy and then allow for sublimation. And this is going to play a role as well in our tropical glaciers. Okay, so now we have on the top side what happens in mid-latitudes and Arctic glaciers. So when mass is lost, it's going to be lost at the front of the glacier, and glaciers are going to retreat to high elevation. Ice caps or ice sheets are a bit more complicated. They lose mass over the entire area, and they are going to move as a result. I'm not going to spend too much time on this. Tropical glaciers, as they are now, there are almost no ice movement. And so when they lose mass everywhere. On the left here, they lose mass over the entire area. You see the gray area is what has been lost by the glacier. And on the Kilimanjaro plateau, they lose mass at the surface, and they lose mass from the side, mostly via sublimation and a little bit via melting. And so this has driven a lot of research over the past 20 years because of their symbolic nature and their really importance. These glaciers have many more scientists working on them and measuring them, and publication talking about them than any other glaciers, I would argue, in the world almost. And scientists are looking at all the processes which are leading to mass loss. And this involves looking at the very detail of this glacier. For example, here, Kibo Glacier on Kilimanjaro again. It involves looking at what is the state of the atmosphere above the ice. How does an ice cliff react to changing atmospheric conditions? Here you can see also what is called penitentes in South America, which are structures which are very indicative of sublimation processes, the process I was talking about earlier. And of course, I'm not going to bore you with all the details here because it's going too far, but scientists then have spent a lot of time explaining that these glaciers are not going to react to temperature change in the same way than glaciers in the mid-latitudes. They have really found that what's really playing a role is whether or not snowfall is occurring on the glacier to protect the glacier surface. And so they have used atmospheric models here, for example, to show that the drying in the atmosphere leads to way too dry conditions at the top of the mountain. Here, this is a symbol and symbolic, a synthetic Kilimanjaro. And if you have positive conditions in the atmosphere to encourage so moist atmosphere, then it's likely that maybe some storms are going to reach the top of the mountain. While if you have dry conditions in the atmosphere, which is becoming more and more prevalent in this region, then precipitation cannot occur at the top. And the glacier is left then losing mass via sublimation and other processes because it doesn't have this input from snowfall anymore. And so when we put this into the big picture and we look at what has changed in the region, we see that air temperature did increase in the region, but here looking at data only at approximately 1.5 kilometers above sea level. And here we see, so from the 50s to today, a very distinct warming, which is due to the anthropogenic climate change. In high elevation, however, if we look at 600 hectopascals, that is above 4 kilometers to 5 kilometers where these glaciers are located, it's not so clear signal of temperature change. This is because the Earth is more likely in the tropics to warm close to the ground. However, looking at specific humidity, so this is a measure of humidity in the atmosphere, we see a very strong decline over the entire 50 years, and probably also earlier because we have seen these glaciers losing mass even earlier. And scientists then have hypothesized why are we seeing this drying. So there are various explanations in the literature. One of them is a change in the atmospheric circulation in the Indian Ocean, which was not related to climate change as first, but is now related to anthropogenic climate change. This is definitely part of research which still needs a bit more interest and research from the community. And this brings me then to the end of this short presentation about Africa's glaciers from a scientific point of view. We observe a constant and dramatic area decrease of tropical glaciers, indicating that they are going to disappear in the next decades anyway. This retreat has received high public attention. It is important. It is related to climate change, but maybe not to temperature as is the case in other regions, but it's related to drying in the mid-troposphere, so in the middle of the atmosphere, which has ties to climate warming and illustrates also how global warming is not only just a scale like we have on these pillars here, but indicates other dramatic changes in the atmosphere. The area changes we are seeing is mostly due to this drying and changes on the Earth's atmosphere interface, such as darkening because less snowfall is coming to the glacier. And then the additional warming that we are seeing in very recent years is also starting to play a role and is maybe accelerating the demise of these glaciers. With this, I'd like to conclude, and I'm happy to take questions if there are some. Thank you for your attention. Other questions? If not, we can also have a chat by the side.
Hello. Thank you for your presentation. I could see some parts of it, but I got interested in the kind of a comparison you did between Arctic and these mountain glaciers in Africa. So my question is in regard with the what would be the assumption for the refreezing magnitudes in this type of mountain glaciers? Because, for example, in Greenland, the whole hydrological budget for the discharge could be could bear certain errors if you don't consider the refreezing patterns. So I don't know if in this case the assumption would be that it's relevant because maybe the crack size or the geometry would not play a role in this.
Okay, thank you. So the question was about a process which we call refreezing, which is when melt occurs at the surface of the glacier, which is at the melting point, and then this creates liquid water, which then percolates through the snowpack. And when it percolates to the snowpack, it reaches colder layers of snow and then refreezes. And this is what we call refreezing. This is an extremely important process in the Arctic because we have exactly these conditions: melting point at the surface and colder conditions well below, because in the Arctic, well, it's cold, especially in the winter. Refreezing is almost not happening in these glaciers because almost no melt is happening. So most of the ice loss is going to be by sublimation. It's taken into account by these models. So all these processes have been studied, but it's a relatively small process in these regions. Yeah. I forgot to mention the water resources topic because there have been also confusion. Only 20 years ago, there have been some confusion about this, but people were worried about the fact that these glaciers are disappearing and then the Nile is going to dry, or the agriculture downstream is not going to have water. But these glaciers are so small that they play actually no role at all in the hydrological system. So their role is mostly symbolic, and they play this role very strongly and importantly, but for water resources, it's not so important. Good. Thank you for your attention, and I hope you have a nice rest of the COP. Thank you.